Okay, so I'm going to talk about shock tube and RCN contribution to mechanism generation and validation. Okay, so here we have an engine. Okay, we have an intake stroke where the piston descends, sucking in air into the cylinder through an open air intake valves as fuel is injected. Okay, 2, we have a compression stroke where all the valves are closed. The piston comes back up, compressing the fuel air mixture to top dead center. Compressing the mixture delivers better power and efficiency. Okay. 3, we have this power stroke. Spark ignites the compressed fuel air mixture. The resulting gas expansion forces the piston to bottom dead center. Okay. And then we have the expansion stroke. The piston comes back up, pushing the exhaust gas out through the exhaust valves. So you've got these springs which help that process. Okay. So you've got a 4-stroke engine. Okay. So, and this would be then a typical in-cylinder pressure versus crank angle degree. Okay. So here we have the pressure. We don't start at minus 180. Okay, minus 60. The pressure comes up to about 80 bar, and then plateaus there, and then it ignites. You get fuel ignition. Okay, and so it plateaus here up to 0 crank angle degree. The piston reaches top dead center, and then we get ignition. Okay, so we've got 2 different experiments, and then the model prediction of those experiments. Okay, but what we plotted here is pressure versus crank angle degree. But what is crank angle degree? It's actually time. If we know the revs per minute of the engine, the operating of the engine, we can convert this crank angle degree to time. Okay, and roughly speaking, if we translate this crank angle degree to time, this period from about here to here is about 1 millisecond, or a half a millisecond. Okay, between a half and 1 millisecond. Okay, so depending on the engine operating speed, right? But anyway, so we need to study kinetics in engines. We need facilities that will study kinetics at that time scale. Okay, so I just showed you jet stirred reactor there and flow reactors. You're talking there on second time scales. Okay, we like, and also here the pressures are 80 bar here at the end of compression. So we want a facility that can measure up at 80 bar. Okay, and the time scales that are involved there. Okay, so the facilities to study these typically that are used are rapid compression machines and shock tubes. Okay, so rapid compression machines, we can study time scales up to about half a second on the millisecond time scale. In shock tubes, typically the order of millisecond down to microsecond time scale, 50 microseconds or so. Okay. And of course, we also use data from jet stirred reactors and flow reactors, as I've just shown you, and also flat flame burners to measure species profiles. Okay, so I'm just going to focus on the rapid compression machine. This is a cheat. It doesn't look like this anymore. This is when it was brand new, and it was just put into the lab. Okay, and we have a dual piston machine. So we have a piston on this side, piston on this side. Here's the chamber to which the pistons inside the sleeves here compress the gas into that chamber. So initially, the pistons are drawn back. I have it here. So this is a schematic of it. Okay, these are the pistons at top dead center, fully compressed. Okay, so we have a hydraulic chamber here. We've got the cylinder, and we have the reaction chamber. Okay, so we draw back the pistons. After we draw back the pistons, we enter a sample of our test gas into this space. Okay? Then we we draw them back. We lock the cylinders in place using the hydraulic chamber. And then we release the pressure on the hydraulic chamber, and the pistons shoot forward, compressing the gas to high temperature and pressure. And when the pistons come forward, we have a pressure transducer on the chamber here that measures the pressure versus time, okay? We take the time at the end of compression to the time to auto-ignition. That's our ignition delay time, okay? And you can see, look, there's a kind of a peak here, and then the pressure drops a bit, and then it rises again, okay? So everything isn't ideal, okay? Everything isn't ideal, okay? This is just showing you, again, I'm just showing you a close-up. These are, so here we have the piston sleeves, here's the piston shaft, and here we have the pistons, okay? And you can see here they're creviced. Yes, okay? I'll be talking about that in a minute, okay? So here we have crevice pistons. So the tolerance here is very, if you can see it, I don't know whether you can, there's a taper here of about 4% on the piston face, okay? So this is very close to the wall. So the boundary layer that's on the wall gets entrained into this crevice here and doesn't get entrained in front of the piston into the center of the chamber, okay? And that's important, okay? So, and then this is just showing, this is the side of the chamber here. This is looking at it face on, so the piston sort of comes up to this face on either side, and the gas gets compressed into this volume at the end of compression, okay? So it's quite a small volume, yeah.
So was this in a specific manner?
Well, I don't know. The reason it makes everything symmetric, okay? If you have just one, it's not as symmetric, okay? And we'll see that in a second. Okay, so this is what I was trying to see here about the boundary layer. So we're looking at, we'd say, that right-hand piston, okay? And the piston is moving in this direction here. So here we have the boundary layer gas. If we have a crevice piston, the shaft shoots forward, the piston's ahead of it. Here's that taper that I was talking about. And your boundary layer gas gets entrained on this face and then gets entrained into the crevice, okay? Whereas if we have no crevice, okay, your boundary layer, okay, gets entrained in front of the crevice. We get this roll-up vortex, and we get an inhomogeneous temperature gas in the center of the chamber, okay? And this was actually simulated by Judith Wormel and John Simi and published in 2005. So this is a simulation, courtesy of Judith, that shows that, okay? And it's just two simulations. So you'll see again, so here on the left we have a flat piston, here on the right we have a crevice piston. And just see the temperature field of the gas inside the chamber at the end of compression using the flat piston and the crevice piston. So you can see here, first of all, you have homogeneity using the dual piston. It shows you've got 4 pockets, right, where the 2 pockets of gas, and you have the center line of symmetry in the center of the chamber when you've got the 2 things synchronized, okay, which is nice, okay. Here, when you got a PDF version, but in my version, I was going to say if you run this, you can see it again. But here you've got the crevice, and so your piston's coming forward from this side on this way, the piston comes forward on this side and this way. Here you see the crevice on the back side, the other side, okay? But you can see that the gas is inside the crevice here, okay? And you have a much more homogeneous temperature field at the end of compression with the crevice compared to the case without it, okay? So in the case of the flat piston, the crevice gets entrained. You've got this roll-up vortex where the gas gets entrained into the center of the chamber. So you've got that cold gas making an inhomogeneous temperature field at the end of compression, which isn't ideal. Okay. Okay, so this is then a typical pressure time history. It's a bit more close-up from what I showed you a little bit earlier. And you can see here, this is time zero at the end of compression. There is a little bit of pressure drop, and then you've got this rapid rise in pressure due to ignition. Okay, so typically we report the time, this is our ignition delay time, the time from the end of compression to auto-ignition. But you have to be very careful because in a rapid compression machine, what is time zero? Time zero is actually just when the pistons start to move, right? It isn't really the end of compression. If you wanted to define time zero and simulate the whole experiment, you should simulate it from when the pistons start to move. That's time zero, okay? So time zero actually should be back here, okay? And then you can simulate the whole thing, okay? The compression and expansion. Well, compression and constant volume, okay? But I just slipped of the tongue there. I'll show you what we're going to do, okay? So if we look here, this is P over the relative pressure on the y-axis versus time. So we have P over the pressure at the end of compression. So initially, at time zero, it's very low. Then only in the last 2 to 3 milliseconds, we get a rapid rise in pressure up to the pressure at the end of compression. But then the pressure decays with time. And this is in seconds, so this is 400 milliseconds. Okay? So it isn't ideal. Okay? So the piston does stop. We've compressed the gas to 6, 8, 1,000 Kelvin. 600, 800, 1,000 Kelvin. Okay? But the walls are at room temperature, or it may be possibly at most, we heat it maybe to 100, 150 centigrade. Okay? So you're talking about possibly 370, 400 Kelvin, something like that. Okay? Maybe max. Okay? But the gas is at 800 to 1,000 Kelvin. Okay? So that gas, what's the heat capacity of the gas then? If you have a mixture in argon, it's not great. Particularly if your gas then is 80% argon, right? It's losing a lot of heat very easily to the walls. Okay? Hence, the pressure drops. So how do we account for that pressure drop if we want to simulate a rapid compression machine experiment? Okay? We have to try and do something with it to simulate it. Okay? So in this part, we want to simulate the compression, and in this part, we want to simulate the heat loss. Okay? So what we do is we actually convert the pressure time history into a volume time history. Okay? So we start off, this is the relative volume profile, the blue line. Okay? And so the volume is very large at the start. It has the most volume. Okay, the pistons move. There isn't much change in volume. Then in the last few milliseconds, we get a huge change in volume down to a very small volume. And then the volume seems to increase again, right? This is just converting the pressure time history into a volume time history using this relationship. P2 over P1 is equal to V1 over V2 to the gamma. Okay? Where gamma is about 1.34 or so. Okay? Now, so what does that do? It means essentially that we're treating, this is end of compression, this point. So we're treating the compression, the point up to the end of compression as a compression. but we can treat the point after compression as an expansion, a volume expansion. Okay? So in other words, we convert this pressure time history into a compression and then an expansion. So in reality, what happens is the pistons shoot forward, the pistons stop, and that gas is losing heat to the walls. To account for that heat loss to the walls, what we assume is the pistons shoot forward, they stop, and the pistons are relaxing back a little bit to account for that pressure drop in the simulation. That's not what happens in actuality, but that's what we do to simulate it. Okay. And so we take, there's no point in taking multiple points along this curve because the volume here and the volume here are the same. So we take enough volume points so that we have enough detail to provide for the input for the simulation. Okay? And then that input is used in ChemChin as a volume time history. So we can then provide that volume time history so that we can then extract the chemistry. So we have the facility effect, which is this pressure time history, which is converted ultimately into a volume time history, but it's giving us the pressure time versus time. And then we combine that with the chemistry in the simulation to simulate what actually happens in reality. So in reality, if you have an accurate model, you start the simulation at real time zero. Not end of compression, but at the start of compression. And you allow the gas to be compressed and then expand a little bit so that you simulate what actually happens in the experiment. And that's what we do when we simulate a rapid compression machine experiment. Okay? Okay. So, and we assume that the temperature and pressure are related by T over Ti is equal to P over Pi to the gamma minus 1 over gamma. Okay. Okay. And if you do that, okay, you've got this, if we just look at it, you've got this temperature versus time history. This temperature versus time, the blue line, came from that equation that I just showed you. Okay? And this is what Professor Jackie Sung's group did in 2014. Okay? And then they did something really nice, right? So they did two-line thermometry and H2O measurements in a rapid compression machine using laser absorption at 7.6 micrometers. Okay? And what they were able to do is you measure the water absorption as a function here of wave number at different temperatures. Okay? So it's just, they took a mixture then of argon with just less than 3% water in the mixture. And they looked at the absorption of the water as a function of temperature. So they did a series of standard experiments first. And this is the kind of profiles that they saw. And then, so here they had 663 Kelvin, here's 1896 Kelvin, here's 1008 Kelvin. And then you can interpolate in between. Okay? And then they said, okay, let's do an experiment now in the rapid compression machine, measure the absorption due to water, and back out the temperature based on this, the absorption measurement. Okay? And these are the red points that they got for those experiments. And you can see that the red points coincide with the translation of the pressure to temperature based on that isentropic relationship. Okay? So this is showing you that what this translation of the pressure into a temperature time history is actually very good. Okay? And it does give you a measurement of the temperature inside the chamber. Okay? Because we can't measure the temperature, we measure the pressure in the chamber. Okay? But if we use that relationship, we can convert the pressure into temperature. Why are we concerned with the temperature time history? in a rapid compression machine? Exactly. So the answer was, it's going to affect the kinetics based on the Arrhenius equation. Remember that the rate of reaction is exponentially dependent on temperature. So we want to know the temperature very accurately. And that's why we want this. Okay? So this was a very nice proof that, yes, doing this conversion of pressure into temperature, and if you do the temperature measurement, they coincide. Okay? So it's a very good measure. So there's a good agreement within plus or minus 5K. Okay. So that's how we can simulate experiments in a rapid compression machine. Not only can we measure then, so typically, my group, we measure ignition delay times. Okay? So we're just measuring, okay? And we do report ignition delay time from the end of compression to ignition. Okay? But we can simulate the time up to the end of compression as well. Okay? So really at the start of compression, right up to ignition. Okay? And that's what we do when we do the simulation. Okay? So, but other groups, so John Griffiths in 1980, they were the first to use a rapid compression machine actually to measure species profiles. Okay? It was back in 1980. So here you have a piston. So and John Griffiths, the rapid compression machine in Leeds was pretty much a clone of the machine that we have in Galway, which came originally from Shell Thornton in the UK. So the machine I showed you a picture of is a clone of the original Shell Thornton machine. Okay? And it is a dual piston machine. The one in Leeds is a single piston machine. So they just took a half of it, like you were asking earlier. Okay? And so here the piston shoots forward, it comes to a rest, and your gas is in this pocket in here and reacting. And then you have a diaphragm here. You use this plunger to burst the diaphragm, and that quenches the reaction at different times. And then your gas expands into this chamber, and you can then take your gas and analyze it. Okay? So that was the idea. Okay? And something similar was done in Lille in 1994, quite a bit time later. Okay, similar idea here. You're expanding into, or compressing into here. Here's your solenoid valve, bursting the diaphragm here. Your gas is coming out here, expanding into a chamber. Similar idea. Okay? Margaret Rutledge's group have a rapid compression facility. Okay, so they use this sabot to compress into this small area, and again, they have a test volume here, and they can sample gases from that facility. Okay, just showing you that this is done pretty routinely now. Okay, and this is just looking at light emission as well. So here's just a pressure time history from it, but here's light emission. Okay, and you can see the rise in light emission and the rise in pressure are coincident. Okay, and you're getting a very, so here's the onset, ignition is just starting at 6.562 milliseconds. It's very intense. Okay. Okay, so that's rapid compression machines. Okay, what about shock tubes? Okay, so shock tubes are facilities. You've got a driven section and you've got a driver section, separated by a diaphragm. Okay? And they can measure wide ranges of temperatures and pressures up to 2,000 Kelvin, 50 bar are routine. Okay? So let's look at it. So I'll just show you here. This is from NIST. It's just showing you the dynamic pressure sensing with the shock tube. So here's the driver, and here's the driven section. So you see you have a high pressure gas here and a relatively low pressure of test gas in this side. So you have a high pressure, typically maybe helium or hydrogen driver gas. Okay? We use helium all the time. Okay? So the low pressure section be low pressure test gas. And here's the diaphragm. It separates the two sections from one another. And we have pressure transducers here in the wall so that we can actually measure the arrival of the shock wave. Okay? So when this diaphragm bursts, a shock wave is developed because you've got such a differential in pressure between the high pressure and low pressure section. Okay? So you've got some sort of a membrane. That membrane is going to burst. Okay? The pressure wave is released, and that wave travels at twice the speed of sound, typically Mach 2 or more. Okay? So it travels very quickly through the gas. The gas moves a little bit, but in the frame of reference, not relative to the speed of the shock wave, it doesn't really move much. Okay? And so the gas gets compressed. When it gets hit by the shock wave, it gets compressed to a higher temperature and pressure. You see it here. And then the shock wave reaches the end plate, reflects back, and heats the gas to an even higher temperature and pressure. Okay? And you see here the different... you can go to this, the website, the NIST website, you see this. Okay? So that's that. Here is another slide depicting the same thing from Professor Christoph Schultz's group in Duisburg. Okay? So we burst the diaphragm. Okay? So the idea here, just to visually show you, when you burst the diaphragm, the incident wave heats it to a middling temperature and pressure. The reflected shock heats it to an even higher temperature and pressure. So it's orange and red. Okay, is the idea. Okay? Now, one thing I want to show here. So your shock heats the gas to this temperature and pressure, reflects back, and then heats to another temperature and pressure here. Okay? Okay, I'm going to say it here first. So when this diaphragm bursts, there's an expansion fan. Okay, the shock wave goes in this direction, but there's an expansion fan that goes in the reverse direction. That expansion fan hits the end plate, and it reflects off the end plate, and then travels back this way. Okay? And that expansion fan then catches up with the reflected shock, and they annihilate one another. Okay? And so if you want to analyze a gas behind the reflected shock wave, would you like to look at the gas here or here? Which would be best? At the end wall. As close to the end wall as possible. Okay? Because your gas is at those ideal conditions for longest. Okay? And so always in a shock tube, we analyze the gas here at the end wall. Okay? As close to the end wall as possible. Okay? So this is just showing another one. Here, I'm showing you the pressure. So here we have a pressure transducer in the end wall. Okay? The pressure is 0 at the start, or very low. It's not quite 0, but it's measuring the pressure of the driven gas, which is low. Okay? The shock wave reaches the end plate, gets reflected back. There's a bit of noise and ringing and so on. And then it stays pretty constant, and then we get this rapid rise in pressure. So this is the arrival of the shock wave at the end plate. This is rapid rise due to ignition. The time differential between from here to here is the ignition delay time, characteristic ignition delay time of the fuel. Okay? Okay. But we can also analyze species profiles in here. Okay? So the fuel decreases in time. Okay? These are just predictions now. Okay? So here's time 0, your fuel decreasing in time. And also intermediates and product species, okay, CO, CO2, increase in time, okay? And so they can all be measured. This is another simulation just showing you, look, here's the pressure profile, and here's the temperature profile. We might look at the temperature profile. It'll be easiest to follow, okay? This goes through again and again. So here we're at room temperature. The diaphragm bursts. The incident temperature rises. Shock wave reflects back. The temperature rises again. But it doesn't stay constant very long because the expansion fan, the refraction wave, catches up and annihilates the whole thing, okay? So you're stuck. And this is showing you that, okay? So here we have, it looks complicated, but it's simple, okay? So don't get intimidated. Here is the diaphragm position. So this is position along the shock tube, okay? So this is the end of the driver section, sorry. Here's the diaphragm position, and here's the driven section, all right? So we burst the diaphragm, the shock wave travels to the end plate, reflects back, hits the end, and then reflects off that, okay? But when the diaphragm bursts, we have this expansion fan, and that travels in the opposite direction, hits the other end of the shock tube, reflects off that, and then travels to the other end of the tube. So here's our shock wave, hits the end plate, reflects back. So our gas here is now at the reflected shock temperature and pressure, times 0 for the reflected shock temperature and pressure. And then this is time on the y-axis, okay? So the time from here to when this expansion fan hits the end plate is the time that we can study the gas ideally behind the reflected shock wave, okay? Any time after that, we can't, okay? Because it gets annihilated. And that's why you're limited in time. So if you see the Stanford shock tower, I don't have a picture of it here, I should actually. They have a tube, they have a tube where the driven section, go back. I should include it. So this driven section has a U-bend in it, and the tube comes around like this. So that they have a much longer time for the expansion fan to come around here, hit the end plate, and then come back, okay? And that will extend the time that you can study the gas behind the reflected shock. They also have other things that they can do, putting in inserts and so on, okay? So the longer this driver section, within reason, then the longer that you can study the test gas here. Of course, it's not going to stay ideal forever, okay? It's going to lose heat to the walls and so on. Okay, but within a time scale. So actually, Stanford have measured times up to about 80 milliseconds, okay, test time. Okay, but it's more standard in shock tubes to measure possibly up to 5, typically 1, 2 in our facilities in Galway, but typically maybe up to 10 milliseconds would be pretty, with tailoring and so on, you can get up to there readily. Yes, it's more ideal.
Right, because
Yes.
shorter now that the time scale.
Yes. So you don't really have to consider the heat losses. Yeah. And also, oftentimes, the relevant time scale. Remember I showed you there, the fuel was igniting in a half a millisecond. You can study up to maybe 5 milliseconds quite easily in a shock tube. So you can study those kind of fuels easily. Okay? But if we look then, so here's our shock tube, here's the end wall, shock wave, it's this, reflects back, so we study the gas then as close to the end wall as possible. But if we have a window in the end wall or a window in the side wall, and we look for light emission, for instance, just as an example, What you see in the end wall is something like this. No light emission for a period of time. And then the light emission takes off, and you see this kind of slow decay because you're looking down the tube, right? However, if you look in the side wall, you're looking at the test gas just in this pocket across here. So again, you see the same delay. It'll be slightly longer, okay? Because your reflected shock wave takes a slightly longer time to reach here as opposed to here, okay? Anyway, your fuel ignites, emitting light, but then all the fuel goes away. And so it reaches a peak and down again, goes back to zero. So if you're looking across the tube, you see something like this. If you're looking down the tube, you see something like this. Because you're looking down at all the pockets of gas that are igniting down the tube. But they've been hit by the reflected shock wave slightly later in time as you go down the tube. So they're all igniting with the same characteristic ignition delay time, but it's just that they've been hit by the shock wave a little bit later. Okay? If that makes sense to you. Okay, yeah? No. It does affect the kinetics very slightly. So you'll see a slight difference in nitrogen as opposed to argon. But that's more third body effect than it is anything else in terms of kinetics. Okay? But it's very minimal. Okay? It does, like the heat capacity allows you to reach different temperatures. Okay? So we typically study the fuels in argon diluent rather than nitrogen diluent. It's just that we're in the temperature regime that we want to be in. Okay, so here's a typical then pressure time history and light emission history for a shock tube experiment. Okay, and here you can see, look, I've drawn an horizontal line here. Okay, and you can see that the pressure is staying pretty constant from the end from the arrival of the reflected shock wave to the end, to ignition. Okay, and the light emission and the pressure rise are coincident. Okay, and the ignition delay time here is about 22 milliseconds. Okay, and so using shock tube and rapid compression machine data, you can measure a wide range of temperature. But actually, it's time. It's a wide range of time that you're measuring. Okay? Remember, the time scales in the rapid compression machine are millisecond. So you're talking about 5 millisecond up to half a second. 100, 200 milliseconds, fairly standard. Okay? Whereas in the shock tube, here the data are going out to here it's 3 milliseconds or so, down to about 100 microseconds, maybe 50, something like that. Okay? So it's time scale that's giving you the higher temperatures. Okay? Shorter times, higher temperature. Longer times, you're at lower temperature. So, but by using both facilities, you can measure a wide range of temperature for ignition delay times. But remember, it's the time scale that you can study that's important. So longer times, typically you're at lower temperature. Shorter times, you're at higher temperature. Okay? But using the two, they can be very complementary. Okay? So in rapid compression machines, typically we look at fuel and air mixtures of the order. It's just a kind of rule of thumb. It's not precise, right? 600 to 1100 Kelvin, shock tubes about 1100 to 2000. So using both facilities, you could go from potentially 600 to about 2000 Kelvin is the idea. Okay. Okay. So here's something. I'm a bit delayed today, but we'll finish and we can finish it again tomorrow morning. Okay. We do another 5 minutes and then I finish. Okay. Here's something though. I published in 2008. Okay, so here are ignition delay times that we measured in a rapid compression machine for propane. And here were data that existed in the literature up to that point for propane measured in a shock tube. And if you're at 900 Kelvin here, there's 2 orders of magnitude difference in measured ignition delay time. Okay? Not so good. Okay? And this was the model prediction that I published in this paper. Okay? We had taken the rapid compression machine data, and these are reputable groups. You know, these guys pretty much, you know, they knew what they were doing. So it was like, when we came to the reviewers, normally at that time we might get 3 reviewers. I had 5 on the paper. And all of them said, nice work, but can we trust this data and its new results from this rapid compression machine and so on? Okay. So it's really weird with this 2 orders of magnitude difference and so on, what's going on? Okay. Because I was asked earlier at the break, you know, if you're in a jet stirred reactor or a flow reactor, what's the difference in the kinetics? And there should be none. Like the characteristic reactivity of a molecule, if you're at that temperature and pressure, should be the same no matter what facility you're in. Okay? It'll react at that rate. It has a characteristic. We're using the facility to measure the rate at which it reacts. But it doesn't matter what facility you use, it should react at a certain rate. Here, there's 2 orders of magnitude difference in reported rate of reaction for the same condition. Something wrong, right? Okay, so on mature reflection, this is the pressure time history that I showed you a little bit earlier. This is actually a propane air mixture from Eric Peterson's experiments, right? And unfortunately, I don't have the one from in here, but this is a pressure time history for methane-ethane mixture under a similar condition. So this is at 1,000 Kelvin. But if you go lower, A27 Kelvin, 20 atmospheres, okay? You see, here's the arrival of the reflected shock wave. The pressure stays constant up to about 5 milliseconds, okay? And then beyond that, the pressure starts to go up, and then it ignites, okay? If this pressure is rising, what's happening to temperature? It's increasing also. So, and what happens to the rate of reactivity of that fuel mixture? It's increasing with that temperature because it's exponentially dependent on temperature. Yet, when we traditionally simulated this experiment, we assumed that the pressure was flat up to here. But it isn't, right? So, hence, you report an ignition time down here because you'd have pressure rise. Whereas if it was flat, you'd have this reported ignition time. And this is what's happening. Okay? So when we went back and we asked the people in Duisburg to look at their pressure time histories, they saw exactly this kind of pressure rise. Okay? And there's nothing you can do about it. That's the nature of the beast. Okay? And we actually, as a community, we don't know what causes that. But it happens sometimes. Okay? Okay? And it typically happens at these pressures, like these high pressures, and around the 800, 900, 1,000 Kelvin. It seems to go away again at higher temperature. But if you're in for particular fuels at these particular conditions, it seems to happen. But it's not fully understood why, right? But if it does happen, then you're not at this ideal condition that you think you're at, okay? And it's affecting your thing. So, okay, so I'll go on. Okay, so all of these data suffered from that early pressure rise, okay? So then this is a simulation courtesy of Professor Alex Heufer now in Aachen University, but he was a postdoc with me. And he used a model that we had at the time to simulate, these are the RCM data again, And these are the shock tube data again. Okay? But now here's a model. So if we do a constant volume simulation of it captures, this is the blue line, it captures neither data set, right? So neither facility is ideal, right? So this is ideality, and neither of them are ideal, right? Both of them have their flaws, right? The RCM, we've got heat loss. We have to include that by putting in this volume expansion simulation, okay? But when we do that, we get good agreement. But look at this. Here, at this point, the constant volume simulation and the facility effect simulation are the same. But if we go higher, this dashed line, the facility effect simulation is faster than the constant volume. Why? Because look at our characteristic time. We're at 3-4 milliseconds. Your fuel, what are we reporting? This is ignition delay time from end of compression to ignition. And that's 3 to 4 milliseconds. So, but your gas didn't arrive at time zero at the end of compression. It had all the time to compression. And during compression, it's being heated to a higher temperature and pressure. So there's time for a reaction of the fuel. So actually, your fuel is reacting during compression, leading to a faster reactivity and ignition after 4 milliseconds, okay? And that's captured by the model. And if you just assume that it starts at time zero, not preconditioned, the predicted time is longer. I hope I hope that's clear. Okay, so the time actually here that is reported is about 8 milliseconds, not 4. So it's twice as long. So you haven't got a preconditioned gas. You've got your gas starting at that temperature and pressure at the end of compression, but no preconditioning. Okay? Whereas in the RCM simulation, you're starting the simulation at the start of compression. You're including that compression in the simulation. And in the last few milliseconds of the compression, your gas is being heated to a higher temperature and pressure. The chemistry is evolving. And so what would be time zero in a constant volume simulation, your gas has now reacted because it has had that preconditioning. And so there's radicals in there and so on. So it's going to ignite sooner after compression than a constant volume simulation. And that's what we see. Okay? In the same way here, these points can be simulated if we include the pressure time history. So if we allow the pressure to rise, like it does in the observed experiments, then we can simulate those experiments very well with correct chemistry. Okay? So if we have good chemistry, which we seem to have, we can capture the reactivity of both the rapid compression machine and the shock tube, even with these facility effects in place, quite accurately. Okay? And neither facility is perfect. Okay? Sometimes there can be problems with shock tubes. All the time there's a problem with the rapid compression machine in terms of that heat loss. Okay? But if we take these facility effects into account, we can do pretty accurate kinetics. Okay? I'm already 5 minutes over time, so let's finish at that. Okay, thanks very much. Right.